Hello, and welcome to Astronomy 121's tutorial on basic Newtonian cosmology. In this tutorial, I will first go over what Newtonian cosmology is, and the basic picture to keep in mind for the remainder of the video. I'll then describe the derivation of the so-called Friedmann's equation, the basic equation you'll be using. Lastly, I'll talk about the stuff we're not including, and why general relativity is needed to fully understand the evolution of the universe. I'll then go over some simple examples of how to use Friedmann's equation. Before I begin, I'd like to add that, unlike many other parts of this course, the Foundations of Modern Cosmology textbook by Hawley and Holcomb does an amazing job with Newtonian cosmology. I highly recommend that you read it as many times as needed to fully understand it, and ask your TAs about sections you don't comprehend. Also, this is not meant to be a comprehensive cosmology lecture. I'll be assuming that you've already attended the lectures or looked through the notes and attempted to read the textbook. The main goal of this video is to get you familiar with how to derive and solve Friedmann's equation. Lastly, a word of warning. Newtonian cosmology can be derived in a number of ways, and a homework assignment may ask you to do something differently than what has been written here. Do not simply copy derivations from here. Whomever is marking your work may not take kindly to this. So what is Newtonian cosmology? It's a way of describing the evolution of the universe using only Newtonian dynamics. The physical picture looks like the following. Let's start by assuming that the universe always has uniform density at any given time. Then, let's pick one point in space and call that the origin, r is equal to 0, over here. We assume this point is the center of expansion, and material right at this point doesn't move. It turns out it doesn't really matter where we pick this point if the universe expands or contracts everywhere while maintaining uniform density. The mathematical proof for why this is so is covered in the class notes under Expansion of the Universe and Dark Energy, Part 1. We then pick a particle at a distance r from the center of the expansion. This particle will have some velocity going inward or outward along the radial direction. So r will change with time. R represents the radius of this sphere. This sphere is important because the particle mt can be gravitationally affected by material inside the sphere, but not outside. We will track the evolution of the sphere over time, and it will represent the overall evolution of the universe. The energy balance of particle mt is given as equation 1, where m is all the mass enclosed within r of t, and v is the velocity of mt. If the total energy of the particle is below 0, then the particle will reach some finite radius r maximum, and then fall back. If this total energy is equal to 0, then the particle will reach r is equal to infinity with 0 velocity. If this total energy is greater than 0, then the particle will reach r is equal to infinity with some positive velocity. Recall a number of assignments back you did a question regarding a rock that was thrown upwards. This rock also obeyed equation 1, and also had the possibility of either reaching a maximum radius or flying off to infinity either at exactly the escape velocity, where it would end up having velocities equal to 0 at r is equal to infinity, or greater than the escape velocity. Now let's consider the consequence of forcing the universe to always have a uniform density at any given time. The only way this is possible is if every part of the universe expands by exactly the same amount. I illustrate this using this figure. On the left is a universe. It obviously doesn't have uniform density everywhere, but this is a cartoon, so bear with me. On the right, the universe is expanded by a factor of 2. The overall structure of the universe is identical between the one on the left and the one on the right, except all the distances between particles have increased by a factor of 2. We get the same effect if we just took this universe and zoomed in on it. Astronomers describe this sort of expansion as a homologous expansion. What are the consequences of this sort of expansion? One is that for the sphere we made earlier with radius rt, the enclosed mass is always constant. You can see this here. Let's pick this particle here, and this particle as the origin. In that case, our sphere would be denoted by this red circle here. As the universe expands, so does the circle, but the number of particles within always stays the same. So the mass within a sphere is always constant, but density won't be, since the size of the sphere is increasing with time. Now let's consider the red dot here and the green dot here. Initially, the red dot is at a distance x away from the center, as denoted below here. And this green dot is at a distance 2x from this one. Now, after the universe expands by a factor of 2, this red dot is now 2x away from this one, and this green dot is now 4x away from this one. The time it took to do that expansion, delta t, is the same, so the red dot moved with an average velocity of x over delta t, while the blue dot moved with an average velocity 2x over delta t. We find that the velocity of the objects in the universe is equal to their distance from the origin times a constant. This is exactly what Hubble found for galaxies in our universe, so we call this relationship a Hubble law, and the constant the Hubble parameter. The last thing that's important is that since everything expands homologously, the evolution of a single particle in the universe describes the expansion history of the entire universe. We chose both R and M arbitrarily, but that's okay because any particle's evolution will describe the expansion of the universe. This also suggests that we can get rid of particle radii completely and use a so-called scale factor for the universe. It might not seem obvious why this picture could even represent our universe, since it only works if we require that the universe have the same density everywhere, and somewhat less obvious, that matter in the universe is so-called collisionless. The uniform density thing is usually generalized to the cosmological principle, which states that the universe has the same properties everywhere. Meanwhile, collisionless matter is matter whose particles don't interact with other particles one-on-one and give a pressure. Air molecules, for example, will periodically deflect off of other air molecules due to electromagnetic forces, and the planets in our solar system tend to deflect comets around. Now, at the largest scales, all our observations say that the universe has pretty much identical properties no matter where you look. Meanwhile, galaxies are generally too far away from each other to slingshot off of each other and experience a lot of gravitational deflection. So, we can actually assume that the universe follows the cosmological principle and contains collisionless material. So our assumptions are pretty good. Let's go back to equation 1, the energy balance equation. We can now substitute in V is equal to h times r, and m is equal to 4 pi r cubed rho over 3. The first comes from our discussion before about the Hubble flow, while the latter comes from the fact that the sphere has uniform density. We therefore get equation 2, which can be rewritten as equation 3. We could have also gotten this result from integrating the acceleration equation, that's double dot r is equal to negative gm over r squared. This was done in assignment 2. We again note that radius r is arbitrary, so we define the scale factor, a of t, using this equation here. So r of t is the radius of our arbitrary sphere, a of t is the scale factor, r0 is the radius at time t0, and a0 is the scale factor at time t0. t0 is just some time, where we know the values of r0 and a0. We usually take t0 to be the current age of the universe. That's just by convention. We could take pretty much any time other than t is equal to 0 for this. Now we note that the Hubble parameter is equal to the derivative radius r dot over r. And that, by equation 4, is just equal to a dot over a. We can now plug in a of t in lieu of r of t, and we get equation 6. We now know that 2 times E infinity over mt r0 squared is a constant. This is because E infinity is equal to mt v squared infinity over 2, just the kinetic energy at infinite radius. So 2 times E infinity over mt r0 squared is equal to v infinity squared over r0 squared. We don't know what v infinity is for any given initial radius, but we do know that so long as the universe expands homologously, a particle originally at 2 times the initial radius should always travel twice as fast as a particle originally at just the radius, because one will always be twice as far away from the origin as the other. So if that's a constant, we can then set 2e infinity over mt r0 squared is equal to negative kc squared. Now the negative sign and the c squared are for consistency with general relativity, and we'll talk about that later. We make one more assumption, which is ka naught squared is equal to little k, and little k only equals negative 1, 0, or 1. Then we get equation 8. This means when big K isn't 0, a0 is equal to 1 over big K, which is usually not 1. Therefore, only in a flat universe can we set a0 to anything we like. We did this to help simplify our integrations, but we didn't have to. If we wanted to make it so that a0 was always 1, we could keep big K in our equation. Note that what we just did is implicit in question 4 of assignment 7. We finally write equation 6 to h squared is equal to 8 pi g over 3 rho m minus kc squared over at squared. This is known as Friedmann's equation. Now, since this equation comes from a particle energy balance equation, that's equation 1, we can describe what happens if k takes on a certain value. If k is equal to 1, then the universe will reach a maximum characteristic size, a of t, and then fall back. If k is equal to 0, then the universe will expand until a of t goes to infinity, and the derivative of a goes to 0. If k is equal to minus 1, then the universe will expand until a of t goes to infinity, and the derivative of a will go to some constant, which is larger than 0. Now let's switch gears and talk about general relativity for a bit. We know that GR gives a very different picture of how the universe evolves. Instead of galaxies moving through space, space itself is expanding. And instead of just galaxies being pulled back due to gravity, space itself is also being pulled back. While it's beyond the scope of this video, it's entirely possible to get the Friedmann equation using general relativity. In fact, this is how it was first derived. If we use GR to derive the Friedmann equation, we get equation 10, a remarkably similar equation to what we had before. This is actually very surprising, and it has a lot to do with the constraints put on the universe by the cosmological principle, that the universe must look the same everywhere at a given time. We do, however, have one additional term, this lambda, or dark energy term, over here. We also find that k is a curvature term, and this was why we wrote it as negative big K c squared a little while back. It's so that we can describe little k here, or big K if we'd like, as a curvature term from general relativity. If k is equal to 1, the universe has a positive curvature like that of a sphere. If k is equal to 0, it's flat, and if k is equal to minus 1, it has negative curvature like that of a saddle. From the Einstein field equation, we find that there's a relationship between the density of the universe, rho m, and curvature. There's a critical density where k is equal to 0, and if rho m is less than the critical density, k is equal to minus 1, and if rho m is greater, k is equal to 1. An exact derivation of this equation would also include a radiation term, since light also curves space-time, but we're not going to care about it since for most of the history of the universe, this is a negligible term. If lambda is equal to 0, then equation 10 is identical to equation 9, and how curvature term k changes the fate of the universe remains valid. We can then say that curvature is equivalent to density is equivalent to fate of the universe. This is where we get the idea that a closed universe must eventually end in a big crunch, and an open universe must continue expanding forever. Now, if lambda is not equal to 0, this equivalence is broken. We can have closed universes that expand forever, and open universes that see a big crunch. Two more things. We commonly speak of a density ratio, and that's defined as the density of some component of the universe divided by the critical density. Omega m, for example, is rho m over rho c, while omega lambda is equal to this thing over here. And that's just the dark energy density scaled so that it becomes a matter, and then divided by the critical density. We can actually rewrite the Friedmann equation this way, but we won't do that because it's beyond the scope of this video. The second thing we commonly talk about is redshift, which is the lengthening, due to expansion of the universe, of the wavelengths of photons emitted from distant galaxies on their way to us. Now, a photon's wavelength is proportional to the scale factor because as the universe stretches, so does the wavelength of a photon. So the observed wavelength divided by the emitted wavelength is simply the ratio of scale factor now when the light is observed, and scale factor when the light is emitted. The scale factor when the light is observed is today, t0, and we therefore define the redshift z to be this, which we can rewrite to be this. And equation 11 is something we commonly use. With these tools in hand, we can begin to do basic cosmology. So here's a series of 3 questions to illustrate what we can do with the Friedmann equation. First, let's derive the evolution of a critical matter-dominated, that's lambda is equal to 0, universe. If we say a galaxy at redshift z is equal to 10, how old was the universe when the light we see was emitted by that galaxy? So, derive the evolution means find the scale factor as a function of time. Here, lambda is equal to 0, and k is also equal to 0, so we take equation 10, we set 2 of those terms to 0, and we get this over here. Recall earlier we said that the total mass enclosed within a sphere is fixed. Now the mass of a sphere is equal to the volume of a sphere times the density of the sphere, since the universe has constant density. That means that the volume of the sphere at time t times the density is equal to the volume of the sphere at time t0 times the density at time t0. Now we can rearrange to get this. The density at any given time t is equal to the density at time 0 times the scale factor cubed at time 0 divided by the scale factor at time t cubed, where we used equation 4 for the last step. This gives us, using equation 5, and this thing, this. Now, h squared is equal to 8 pi g rho m over 3, because of what we wrote before, which implies that at time t0, h0 squared is equal to 8 pi g rho m0 divided by 3. Again, the zeros mean at t0 today, so we can write this, which we can then simplify to this. At this point, we use an integration technique called separation of variables. We keep dA here, and we keep all other terms that have a in it on the left-hand side. We then move all of our constants on the right-hand side, and then we move t also to the right-hand side. We then integrate both sides, on the left in terms of a, and on the right in terms of t. And we get this as our result. If you're having trouble seeing this integration, refer to Sergey's online video on integration. Now, for this universe, we expect there to be a Big Bang. There's a couple universes out there that don't have them, but we don't consider them in this course. So that means that when t is equal to 0, a is equal to 0, and so this constant that we get out here is equal to 0. We could have also done a definite integral with the same initial conditions. We go from 0 to a of the left-hand side is equal to 0 to t of the right-hand side. These little apostrophes here, those are just to make these integration variables dummy variables, because technically you're not allowed to do the integral from 0 to a of square root of a dA. It's just not legal to write that. Now, if we do some algebra, we can go from this to this, subbing in c is equal to 0. We're going to plot this function at the end of this section. We now determine the age of the universe when a z is equal to 10 galaxy emitted light to us. Plugging our solution into equation 11, we obtain this equation, which we can rewrite as this equation. We could either plug in the known age of the universe for t0, or to be self-consistent, use the age of the universe given by a critical, matter-dominated universe. To do this, we note that the Hubble parameter is equal to the derivative of a over a. We can plug in our solution for the scale factor, which gives us that the Hubble parameter is equal to 2 over 3 divided by t. This gives t0 is equal to 2 over 3h0, and then we just use the current Hubble parameter. This is equal to 70 kilometers per second per megaparsec. Now we note that these two are both distances, so we can convert this using this conversion process here to 2.27 times 10 to the minus 18 1 over seconds. This gives t0 is equal to 9.3 gigayears when we plug this value back into here. We can then plug 9.3 gigayears into the equation we had above, which gives t emission is equal to 0.255 gigayears. Now, this example illustrates a number of common slip-ups to watch out for. The first is that zeros mean values at time t0, and an equation involving values at t0 does not have to hold for all times t. Do not freely interchange t and t0. I'll also mention that t0 does not equal 0. It almost always equals the time today. So for example, for our universe, t0 would be 13.7 gigayears. Always integrate to turn a dot, the derivative of a, into a. There are very, very few situations where doing so is unnecessary. Make sure you don't forget constants of integration, like we used above, and substitute in initial conditions to remove them. Lastly, be careful with unit conversions, and ask yourself if the answer makes sense. If you get that the age of a critical matter-dominated universe is a day, and you know that our universe, for most of its history, looked like a critical matter-dominated universe, then you know that something is awry and you probably made a unit conversion error. Now, let's derive the evolution of an empty, matter-dominated, again lambda is equal to 0, universe. If we see a galaxy at redshift z is equal to 10, how old was the universe when the light we see was emitted by that galaxy? So this is the same question, just with a different kind of universe. So we now set rho m is equal to 0 because it's empty, and k is equal to -1 because the universe is open. We plug that into Friedmann's equation, and we get this, which gives us this, which we then integrate using separation of variables like we did before. And that gives us a is equal to ct plus d. Again, we take a is equal to 0 when t is equal to 0, and that gives us a is equal to ct. We can use the same procedure as we did above, and we find that the z is equal to 10 galaxy emitted its light when the universe was 1.27 gigayears old, and that the current age of the universe is 14 gigayears. Lastly, let's try deriving the evolution of an empty, flat, dark energy-dominated universe. How old is this universe? Let's take the Friedmann equation again, and note that now we set rho m is equal to 0 and k is equal to 0, because it's flat and the amount of dark energy is huge compared to the amount of regular matter. So we can just assume that rho m doesn't really matter in our universe. When we do this, we get h squared is equal to a constant. And if we do the math, and then integrate by parts, we get that a of t is equal to some constant times an exponential to the power of t. When we calculate h of t, we find that it's equal to a constant, independent of time. Moreover, if we plugged in t is equal to 0 here, we don't get 0. In fact, this universe is infinitely old. And by the way, it's not possible to perform a reasonable definite integral in this case. Any universe that has a finite age therefore cannot have been dark energy dominated forever. Finally, let's plot the fruits of our labor. Here I show the solution to the first example question as critical, over here, and the second as empty, over here. I've made it so that the two curves intersect to give the same scale factor and scale factor derivative today, which is about here. Note that dark energy has been set to 0 for both of these. Now, if we assume that dark energy is equal to 0, then curvature, density, and fate of the universe are all linked. Universes with greater than the critical density are all closed, and will eventually end in a big crunch, and universes with less than the critical density are all open, and will expand forever. The critical density is the most dense universe that will still expand forever. No universe can expand faster than an empty universe. All of the other ones slow down. Now, if we do have dark energy, we get a very different picture. The lambda-only universe here in green, that's example 3, actually expands faster than the empty universe. So everything becomes different once you add dark energy, and you have to be very careful about whether or not a question assumes that dark energy exists in the universe. So that ends this video, and I'd like to recommend again that you read the textbook, chapters 10 and 11, and get yourself well acquainted with the equations that I've just presented. For those that are mathematically inclined, you can also try Carroll and Ostley's An Introduction to Modern Astrophysics, chapter 29. Thanks for watching.